Hi, my name is Ethan, and I'm here with Kyle and Logan, and today we are making the numerical illustration for Proposition 47, or the Pythagorean theorem. We're trying to prove that the areas of two smaller squares based off sides BA and AC of a right triangle equal the area of the largest side of the triangle off of side BC. So here we go. So step one, we are stating our givens for the proposition, and we are creating a right triangle based off of those givens with right triangle with right angle BAC. So to do that, and then for the next step, we will be creating squares off of those three different sides. So we will be creating squares BDEC, AB, FG, and AHKC. And we can do this based off of Proposition 46, which states we can make a square by creating circles to make the various points of those squares. We can do this for all three of the different sides, and we will hide all the circles after we're done, so we don't need to see them anymore. For the next step, we will draw a parallel line starting at point A through the square and parallel to line BD to point L to make parallelogram ABDL. And we can do this based off of Proposition 27, which allows us to create parallel lines. And for the next step, we will be making segments AD and FC, and we'll be passing those through the other triangles. And we can do this based off of postulate 2, which, as we know, which states we can make finite lines continuously through the straight lines, as we're doing right now.
Hi, so now what we're going to be doing is talking about these new triangles that we've made. So the proof begins by, angles BAC and BAG are both right angles, and this is proven by definition 22 with the definition of a square, as well as step 2. So BAC is equal to BAG. CA is in a straight line with AG. We know this because of Proposition 14. Angle BAC and HAC are both right angles, BAC, HAC. So basically, these are in a straight line with each other as well, according to Proposition 14. Now, when we look at these triangles, we need to show that the angles are equal and the sides are equal. So angles DBC and FBA are both right angles, as you can see here, FBA. Now, when we add the angle ABC to both of them, they're equal to each other. We know because equals added to equals are equals, according to common notion 2. So FBA plus ABC is equal to DBC plus ABC, which means these larger angles that are created, DBA and FBC, are equal to each other, also from common notion 2. Now, by the definition of a square, we know that line segment DB is equal to BC and FB is equal to BA by the definition of a square. And since we have two sides and an angle, we can show through Proposition 4 that the longer side AD is equal to longer side FC, and triangle ABD is equal to FBC, according to Proposition 4. Now, this is significant because the parallelogram BL that we have turns out that it's the double of this triangle because they share the parallels on this line on AL, on AL, and on the parallel line BD. And we know, according to Proposition 41, that that parallelogram is double that triangle. And the same thing occurs with this square GB and the triangle FBC, because they share the parallel line GC and FB and the same base FB. According to Proposition 41, triangle is half of this square. And because of common notion 2, since the triangles were equal and they are both half of the parallelograms, then the parallelogram and the square are equal. So this square GB is equal to the parallelogram BL. And now we'll be moving on to the second part.
So the next step in order to prove that square GB is equal to square HC is to connect point segments AE and segments BK. And this is justified by postulate 2. And once we did that, angle ACK is equal to angle BCE because both are right angles according to definition 22. Angle ACK and angle ACB added together are equal to angle BCE and angle ACB, according to common notion 2. As well as angle BCK is equal to angle ACE, according to common notion 2. So therefore, BC is equal to CE, and AC is equal to CK. According to definition 22, which is the definition of square. Line segments AE is equal to BK, and the triangle ACE, as shown, is equal to triangle BCK, according to postulate 4, or proposition 4. Parallelogram CL is double the triangle ACE, as shown, according to proposition 41. Square HC is double the triangle BCK, according to proposition 41 as well. So parallelogram CL is equal to square HC, according to common notion 2. Parallelograms BL and CL equal squares GB and HC, according to common notion 2. So therefore, squares GB and squares HC are equal to the bigger square BCED, according to common notion 2. QED.
All right, so just to finish it off, we're going to show this with numbers to show that the values end up being equal. So let's, since we've shown, let's hide these troublesome things. And now let's hide this. So if we create these parallelograms that we discussed earlier, these separate parallelograms, we could show that we look at their values, 446 is the value of this parallelogram, and 486 is the value of this square. So they were equal as we said in the proof. We could show that this square is equal to the parallelogram CL, as we also showed in the proof. And when these are added together and these are added together, then these smaller squares are equal to the larger square. And we can also just through simple addition demonstrate that. So at the end of the day, the square on the side BC is equal to the squares on the sides BA and AC. And that is what we have sought to shown, QED. How do I stop recording?